Okay, so we're going to look at section 6.5, okay, last section we do in chapter 6, and we'll split it up into 2 days. This is on what we call right triangle trig, or trig using an acute angle. If you've done, or you remember like SOHCAHTOA, it's a way to remember something in trig, that's basically what a good part of this section is on. Okay, if you have no idea what I'm talking about, then I'll show you as we go. So first of all, when we are doing right triangle trig, we are going to be working with triangles that always have a 90-degree angle. Any triangle with a 90-degree angle is called a right triangle. In a right triangle, does anybody remember what you call the two short sides? Yep, Mag?
The legs.
The legs, yep. And the longer side? The hypotenuse. And you don't have to, but there are certain letters we usually use. What are the letters that we use to represent the legs? Yeah.
A and B.
A and B. And how about the letter for the hypotenuse?
C.
C. Okay, that's what we just said. The side across from the right angle is the hypotenuse. The other two sides are the legs. What else do we know about the hypotenuse, besides that it's across from the 90? Something else, yeah?
It has to be bigger than both legs.
Yep, it's always the biggest side. Okay, so there's a diagram explaining everything we just said. The two short sides are the legs, the labels A, B, and C. Long side is the hypotenuse. And these other two angles that I've labeled 1 and 2, those are always acute. What do all the angles in a triangle have to add up to? They have to add up 1 to 180. And how much have you already used if it's a right triangle?
90.
You've already used up 90. That means together, angles 1 and 2 have to add up to 90. Which means they have to be acute. Now there is a theorem that we can use to help us figure out sides in a triangle if we don't know them. But you need to know two. Does anybody know the theorem that I'm thinking of? Yeah?
Pythagorean?
Yeah, the Pythagorean theorem, which basically says if you take a leg and you square it, you take another leg and you square it, and you add that together, that's equal to the hypotenuse squared. So if A and B are the legs and C is the hypotenuse, you would write it A squared plus B squared equals C squared. When we start dealing with triangles that do not have a 90-degree angle in them, you cannot use that theorem. Okay, so that theorem only works in a right triangle, which is what this section is all about. All right. Any questions on that diagram or the Pythagorean theorem? So we're going to look at the 6 trig functions. We've already done them before, but this time we're going to define them in terms of a triangle. In terms of a triangle. What are the first 3 trig functions? And these I consider to be more the basic ones because we have buttons for them on the calculator. Yeah?
Sine, cosine, tangent.
Yeah, sine, cosine, and tangent. And if we define these in terms of a right triangle, each trig function is a ratio of 2 sides. It's a ratio of 2 sides. When you have 3 different sides to pick from, you can pick them 6 different ways. Here's the first 3. Opposite over hypotenuse, adjacent over hypotenuse, and tangent is opposite over adjacent. And when I use the words opposite, adjacent, and hypotenuse, I'm talking about the length. So for example, let's say you were doing cosine. And the adjacent side was 5 centimeters. And the hypotenuse was 12 centimeters. What happens when you actually divide and simplify that fraction? What's going to happen there? Yeah. Right, the centimeters is going to cancel out because you're dividing a length by a length. When you divide a length by a length, there is no unit on the final answer. You have canceled the unit. The answer is just a number, no label. That's why when we do trig, we normally don't put the length label because it's going to cancel out. We don't need it. It's not important. Okay? So those are our first 3 trig functions. If you don't remember the names of the other ones, that's okay for now. But does anybody remember what you have to do with each one of those to get the other 3? Yeah? Flip them. Yep. So we take the reciprocal. Does anybody remember the name of the trig function you get when you flip the sign? Yeah? Cosecant. How about the trig function you get when you flip the cosine? Yep. Secant. And the trig function you get when you flip the tangent? The cotangent. Yes. So each one of those trig functions on the right is the reciprocal of the one on the left. Okay. And there's a trick that you can use to remember the 3 on the left. Does anybody know the, it's kind of like a word, like PEMDAS, each letter stands for something? Yep. Sakatoa. Yeah, can you explain what that means?
So the SOH is sine opposite hypotenuse.
Yeah, sine is opposite over hypotenuse.
The CH is cosine adjacent hypotenuse.
Cosine is adjacent over hypotenuse.
And then the TOA is tangent opposite adjacent.
Tangent is opposite over adjacent. Yep, perfect. So Sakatoa is kind of a way that you can remember the trig functions. One time when I asked, is there a way you can remember the trig functions? Somebody said Sacagawea. She's not going to help you remember trig functions. So Sakatoa is what you want to use. And that'll help you get the 3 on the left. And then when you flip them, you get the 3 on the right. All right, any questions on that? So now I want to talk a little bit about these terms that I was using. Hypotenuse, we understand that's across from the 90. But opposite and adjacent, they are what we call relative terms, meaning they're not fixed. The best comparison I can make is kind of like the words left and right. So in this room, left and right depends on which way you're facing. For me, left is the door, right is the window. For you, it's the opposite. So opposite and adjacent are relative to some perspective in the problem. Okay? They are in reference to something. Okay? Compared to hypotenuse, it's always across from the 90. Okay? That would be like no matter which way you face in this room, which way is up. Up is the same. Left and right can change, but up does not. Okay? So that's what I mean by relative terms. Any questions on that? Okay. So, one thing we want to take a look at is if I draw a triangle like that, and then I draw a triangle like that, and I ask you to find the 6 trig functions of this angle, and then find the 6 trig functions of that angle. The question I want to figure out is, does the size of the triangle matter? Okay, so remember, all the trig functions are lengths of sides divided. The one on the right definitely has bigger sides than the one on the left. But how will the ratio of the sides compare? Yeah?
It'll be the same.
It'll be the same.
2 over 2 is the same as 5 over 5.
Yeah, whether you use a larger version or a smaller version of a triangle, if the angles are the same, when you do trig, the answers will come out the same. Size of the triangle doesn't matter. Okay? So what that means is if I ask you to find the sine of 45 degrees, it doesn't matter if it's a 45-degree triangle that's like an inch big or a 45-degree triangle that's 20 feet big. The sine of 45 degrees is always going to be the same thing. Doesn't matter the size of the triangle. When two triangles have all the same angles, in other words, when one is either an enlargement or a reduction of the other, scale factor, they're called similar. So similar triangles always have the same trig functions for a given angle. We're going to try that on this problem. So these are two 30, 60, 90 triangles, and they are labeled to scale. It might not be drawn to scale, but the labels are all appropriate for a 30, 60, 90. Let's use 30 degrees as what we call our reference angle. Think of the reference angle as where you are standing in the triangle. That determines your opposite and adjacent, like your left and your right. Let's find the sine of 30. What did we just say that sine was? It's the what over the what?
The opposite over hypotenuse.
Yep, it's the opposite over the hypotenuse. And in the triangle on the left, what side is opposite the 30?
1.
Yep, could have done the 60, I chose the 30. So opposite is 1, and the hypotenuse is 2. Now what I've done on the right is I made an enlargement of the triangle on the left. Does anybody see the scale factor? It's just a double, yeah, times 2. Yep. Let's do the sine of 30 in a triangle that is twice as big. What side is opposite to 30 in the right triangle? 2. And the hypotenuse?
4.
And what does that reduce to?
1/2.
Perfect. 1/2 is always the sine of 30, regardless of the size triangle. Questions on that? So the point is, when they ask you to figure out trig functions, if you need to draw a diagram to do it, you can draw your diagram any size you want. It won't make a difference. You have to label it appropriately. That's important. And we'll talk about how you would figure that out if you don't know how to get those numbers. All right, so the next question we're going to look at is something like this. Okay, I'm going to give you one trig function, and I'm going to ask you to find all the other ones. If I give you the sine, I've told you a couple pieces of information. Okay, what have I told you there?
Opposite is fine, hypotenuse is same.
Right, I've given you the opposite, and I've given you the hypotenuse. So with that information, you can now label 2 out of 3 of the sides in a triangle. Once you've labeled 2 of the sides, how could you figure out the one you don't know?
B squared plus B squared plus C squared.
Yeah, and what's that called? The Pythagorean theorem. Yep. So once you label the 2 sides that you know from what I give you, you can use the Pythagorean theorem to find the third side. And now, you know all the sides. So you can determine any trig function that they want you to find. But that's the first step. Label the 2 sides, use the Pythagorean theorem, find the third side. So let's try that on this one. So it says the sine is 5 over 6. Okay, since I have enough space, what I'm going to do is I'm going to do all my work on the left, and I'll put all my answers on the right. Now, keep in mind, this whole time, you do not know how big the angle is. We don't know, is this angle 30 degrees, 40 degrees, 57 degrees? We don't know. All we know is a fact about the angle. We do not know the angle itself. Could we figure out the angle from this piece of information? Absolutely. That's tomorrow. All right, so we've got sine, cosine, tangent. Cosecant, secant, cotangent. All right, so let's make a diagram. And you need to put theta in your diagram somewhere. The only thing it has to be is one of the small angles. It cannot be the 90. So you can either put it on the right or at the top. It will not make a difference. I'm just going to put it on the right. Okay. Now, based on where I put theta, what side in that diagram would be labeled 5?
Oh, I know.
Yeah.
On the left.
Yeah, the left side, the height. That's 5. And what side would be labeled 6? The hypotenuse. Temporarily, what can we label the bottom side?
See.
I wouldn't use C, because C is reserved for hypotenuse. We could use A, or we could use, yeah, I don't care which one we use. Let's just use A. And now, can somebody set up my Pythagorean theorem for me with that information that's on the board? Yeah.
A squared plus 5 squared equals 6 squared.
Okay. So A squared plus 25 equals 36. So I squared everything. What would be my next step? Subtract 25. 36 minus 25 is 11. And now your last step to get A by itself. Square root. When you are doing right triangle trig, and you are finding trig ratios, okay, not when you're solving for angles, that's different, but when you're finding the 6 trig functions, we're going to leave that exact. Okay, so A, we now know, is square root of 11. Okay, 2 things we have to worry about with square roots. What's one thing we want to make sure we're careful about with square roots? Yeah?
You can't square root a negative.
Okay, we can't square root a negative. You'll never have that come up because you're always going to be dealing with positive sides in a triangle. So that is true, but that situation will never happen here. But there is other things that could happen. Yeah?
You can't have them in the denominator.
We don't want to leave square roots in the denominator. And if you end up with something like that, you want to reduce it to something like that. Okay, you do need to reduce square roots. In this problem, square root of 11 doesn't reduce, so it's prime, so don't worry about it. Okay, let's start with our sine. Well, that was given. So technically, we don't need to write that one down again. What about my cosine?
Square root of 11 over 6.
Perfect. Square root of 11 over 6. And my tangent.
5 over square root of 11.
So it would be 5 over square root of 11. But we need to fix it so the root's not in the bottom. What do you get when you fix that? Anybody remember? Or how do you fix that?
Reciprocal.
You can't flip a fraction because then it would change its value. Like if you just take a fraction
No,
like
I mean, you would multiply it by the reciprocal.
that would still change its value, right? If you take a fraction and you multiply it by its reciprocal, it's always going to turn it into the number 1. But that's not the number 1. So we can't do anything to alter that value that would change it. But there is one thing you're allowed to do to a fraction that does not change it. Yep.
Multiply the top and bottom by the square root of 11.
Right. If you multiply the top and the bottom by the same thing, you are effectively multiplying it by 1. But the way we're doing it, it's going to cancel the square root out in the bottom. Okay. What would you get in the top when you multiply what you have there? Yep. Okay, so we get 5 square root of 11 divided by, and what's the square root of 11 times the square root of 11? What is it? 11, yeah, it's the square root of 121. That's how you write the final answer for the tangent. Okay, let's do the cosecant. What would my cosecant be? Yeah, that's
6 over 5.
6 over 5. No roots there, so we don't have to worry about any of those issues. How about my secant final answer? Completely fixed. Yep.
6 square root of 11 over 11.
6 square root of 11 over 11. Okay, and now the cotangent. If we're smart about it, we can do this in one step. We started with this, and we changed it to what was circled. What we started with and what we changed it to are equivalent. That's why there's an equal sign between them. They're the same thing. Which one should we flip to get the cotangent? Yep.
First one.
How come?
Because when you flip it, the square root will be in the numerator.
Yeah, when you flip it, square root goes to the top, and you're done. If you flip the final answer, the square root goes back to the bottom, then you have to fix it all over again just to get the same thing. Okay. So there's your 6 trig functions of theta. Okay. Not to be confused with solving for theta. We have no idea what theta is. We did not solve for it. We found the trig functions of theta. Okay. All right, so let's try part B. Part B, find all 6 trig functions. And they give us the 2 legs, 5, 12. 5 and 12. What's the first thing we have to find in this one? Yeah? Does anybody know what the hypotenuse is going to be?
C.
How much?
C.
Okay, that's the letter, yep. How about the number? Yeah. 13, yeah. This is a special situation where all the sides come out to integers. There are no decimals. Does anybody know what you call the situation when all the sides in a right triangle are all nice numbers, no decimals? Yeah? I've never heard the word perfect used, but there are things called perfect numbers. But in this sense, I think there's a different term that they used, but it does still begin with a P. It has to do with the theorem we use a lot in this kind of triangle. Yep. Pythagorean, and the next word does begin with a T as well, but it's not triangle. It's a Pythagorean, nope, not theorem. Can I have another guess? It's a Pythagorean triple. Okay, Pythagorean triple. That's when all the sides in a right triangle come out without any decimals. Another example is 3, 4, 5. There's an infinite amount of these kinds of triangles. But even though there's an infinite amount of them, most of the time you will not have three sides that are all nice numbers. Okay. All right, so let's start with our sine, cosine, and tangent. Okay. Again, not finding the angle itself, finding trig functions of the angle. Okay. What is my sine? Yeah.
5 over 13.
5 over 13. How about my cosine?
$12/13.
12 over 13. And my tangent? Opposite over adjacent, which is 5 over 12. The name of the trig function, that's the reciprocal of sine.
How do you know which one's the adjacent side and which one's the opposite side?
So the opposite side, that's always the side that is farthest away. And the adjacent is the side right next to the angle. That's not the hypotenuse. So yeah, that's important. I'm not sure. I think I talked about them being relative, but I never said which one was which. So opposite is the one that's farthest away. Adjacent is the one that's right next to it. That's not the hypotenuse, because there's always two sides next to every angle. But one of them is already the hypotenuse. Okay. How about, what's the name of the trig function that's the reciprocal of sine? Yeah? Cosecant. And Natalie, what's my cosecant here? 13 over 5. But we don't care. Improper fractions, no problem at all. We can leave that. Okay. How about the trig function that's the reciprocal of cosine? Secant. And in this case, the secant is
13 over 12.
13 over 12. And the reciprocal of tangent?
Cotangent.
Cotangent. And the cotangent for this problem?
12 over 5.
12 over 5. Okay, so you might think, what's the point of writing the 3 on the right if you know the 3 on the left? Well, let's say that I gave you this piece of information, and I asked you to solve for the angle in the triangle. This piece of information directly doesn't help you on a calculator because there is no CSC button. You have a sine, you have a cosine, and you have a tangent. You don't have CSC. But if I tell you the cosecant, that automatically allows you to figure out the sine. You just flip it. If you know a piece of information about the sine, that's good, because you have a button on the calculator for sine. Okay? So a lot of times we have to take one of these pieces of information on the right and convert it into one of the pieces on the left if we have to do something on a calculator. Okay. Questions on that? Okay. So now, let's see if we can figure out these 6 trig functions of 45 degrees. So now you have to make your own triangle. I'm not giving you one like I did in this problem. You got to make your own. Does it matter what size you make it? No. You can make your 45, 45, 90 any size triangle you want, but you have to label the sides appropriately. What do we know about the base and the height in a 45, 45, 90? They are the same. So you can pick any number you want, as long as you use the same number for the base and the height. And once you pick that, you can use Pythagorean theorem to get the third side. So pick any number you want. How long do you want the base to be? Yeah? Okay, we can pick 2, which means the height is 2, which means if you do the Pythagorean theorem, what's 2 squared? 4 plus 2 squared. So 4 plus 4.
8.
So the hypotenuse is the square root of 8, which reduces to what? 2 square roots of 2. Now, because we didn't pick the smallest side we could have for the legs, we're going to have to reduce every problem. Okay, they're all going to reduce. 2's are going to cancel everywhere. If you had picked a 1 and a 1, the hypotenuse would have been smaller, and you wouldn't have had that. But we can work with that. That's fine. All right, now we have to work with a 45-degree angle. Which 45-degree angle do we have to use? It doesn't matter. You can let either one be your point of reference for the problem. Let's use the one in the lower left. Okay. What side is opposite the 45? 2. And what's the hypotenuse? 2 square roots of 2. Okay. What's going to cancel out there? So we're going to end up with 1 over the square root of 2. And that's what you would have gotten right away if you use side lengths of 1s. Now we need to fix that. What's 1 over the square root of 2 turn into when you fix it? Yep. And that is the sine of 45 degrees. Square root 2 divided by 2. And I can check it by typing in sine 45. Okay, calculator gives me that decimal. It doesn't know how to change it to that. But if I type it in, it does show that it is the same thing. Okay. Let's do the cosine. What's the cosine of 45 degrees going to be? Yep. It's going to be the same thing because the opposite and adjacent are exactly the same length. So that's also square root of 2 over 2. And how about the tangent? One. Opposite divided by adjacent is 1. Okay, so let's do our cosecant. Again, if we're smart about it, we can do this in one step because of something we already have out there. Okay. What's the cosecant of 45?
2 square root of 2 over 2.
Yep, which would reduce to
1 over square root of 2. No, square root of 2 over 1, which is just square root of 2.
yeah. If we just take what we had right there and we flip it, we get just the square root of 2. And we're done. How about the secant?
Same thing.
Same thing. And what about the cotangent?
It's going to be 1 again.
That's also 1. Okay, so there's the 6 trig functions of 45 degrees. But you had to make your own diagram to do it. I think in the homework they say something like use definition 6.6 to find the 6 trig functions of something. That basically means draw your own diagram and figure it out. Okay? But that's theorem 6.6, a 45, 45, 90 right triangle. Does anybody remember the other special right triangle besides 45, 45, 90? Yep.
30, 60, 90.
30, 60, 90. Yep. And we're going to take a look at that one next. Okay, so it says use the diagram below to find the 6 trig functions of 30. Well, let's just do 60. Because if I do 30, then I got to do 6 for 30, then I got to do another 6 for 60. That's going to be 12 problems. Okay, let's just do 60. Okay. First of all, when you're doing the kind of trig that we're doing this week, what kind of triangle do you need to work with? A right triangle. Is that a right triangle? No. Okay, but that's a hint for what you're going to need. Based on that, what kind of triangle is that?
Equilateral.
It's equilateral. Tell me what we know about an equilateral triangle. Yeah?
All of the angles and sides are the same.
Okay, all the angles are the same, all the sides are the same. Let's focus on the angles. Okay, tell me more about the angles. They're all what?
They're all 60.
They're all 60. So that's a 60. That's a 60. That's a 60. So now, how could I turn this into a right triangle? And by doing this, I'm going to create a 30.
Just split it in half.
Yeah, we're not going to go through the proof, but if you draw a line in an equilateral triangle from a vertex, right perpendicular to the base, it will automatically create two congruent triangles, which means the angle here is exactly the same as the angle here. If you take a 60-degree angle and split it into two parts, each part that are equal, each part is how much? 30. Okay, so here's your triangle that you're going to need. There's a 30, 60, 90 right triangle drawn perfectly to scale. What's this triangle missing though?
This side.
It's missing sidelines. Does it matter how big or small I make the triangle? No, I just need to label the sides correctly. So let's go back to our equilateral and look at this for a second. We should pick a length for the sides in the equilateral, which is the hypotenuse of that 30, 60, 90. What would be a good number for the length of that side? I would pick a 2 this time, yes. 'Cause if that's a 2, and that's a 2, and that's a 2, we know that this bottom part is congruent. This piece is exactly the same as that piece. So how long is this piece on the bottom?
1.
That's a 1. So that's a 1, that's a 2, and then we can use Pythagorean theorem to get the third side. And that's what it comes out to. Okay, you can check it. Square that, you get 3. Square that, you get 1. What's 3 plus 1? 4. And what's the square root of 4? 2. There you go. Okay, so that's one way to figure out a 30, 60, 90 right triangle diagram on your own. If you didn't let all the sides be 2, that would be okay. Like if you did 3, it would just make that side a 3. It would make the bottom side a 1.5. Not as nice of a number to work with. Okay. So that's a pretty standard right triangle that you'll see. And now I said let's do everything from the 60. Okay. So let's do all our trig functions. Sine, cosine, tan. The only difference between doing the 30 and the 60 would be the opposite and adjacent switch. But you still get all the same answers, just in different spots. All right, let's start with our sine. What's the sine of 60?
Square root of 3 over 2.
Yeah. And what's going to be very helpful is if we can start to remember that the square root of 3 divided by 2 is about 0.866. Okay, we don't need the decimal a lot, but it is helpful to know that 0.866 turns into root 3 over 2 when we're dealing with right triangle stuff. Okay, how about the cosine of 60? 1/2. And the tangent of 60?
Square root of 3.
Square root of 3. Okay, cosecant?
Square root 3 over 3.
2 root 3 over 3. Perfect. How about secant?
2.
2. And cotangent?
Square root 3 over 3.
Square root 3 over 3. Perfect. There's your 6 trig functions of 60 degrees. Any question on that? Okay, if you did the 30, you would see a bunch of your answers switch places. That's all that would happen. Okay, let's look at this. I think this is the last thing. So this talks about something I think we already kind of mentioned. When you draw a right triangle, it's saying that angles 1 and 2 are always complementary. Why? Why are the two acute angles in a right triangle always complementary? What would happen if they weren't? Yep.
Because the sum of all three angles have to add up to 180 degrees, and if one of them is 90, then the other two have to add up to 90.
Perfect. Yep. The other two have to add up to 90 to be complementary. Yep. Any question on that? Okay. Now, I've been labeling them angle 1 and 2. That's not how they're normally labeled. Okay, when we label an angle we don't know, what kind of letter do we normally use in trig? Theta, or in general, that's what kind of letter is that from?
Greek.
It's a Greek letter. Yeah. So when we are labeling angles that we don't know in a right triangle, well, A, B, and C are the sides. So we're going to stick with lowercase a, b, and c for sides. We're going to use the Greek letter alpha to represent what's across from A, and the Greek letter beta to represent what's across from B. Not every book uses the Greek letters. Some do it differently. Some use capital letters for sides and lowercase letters for angles, or vice versa. What do you think the issue with using capitals and lowercases could be?
C.
Well, yeah, some letters look the same. So if you don't use A, B, and C for your sides, and you use a letter that looks similar when it's lowercase and uppercase, that's a problem. And the other thing is, if I ask you to look at something and I say, look at B, and I'm not clear, you'd be like, well, wait, does he mean the capital B or the lowercase b? Which B is he talking about? All right, so it eliminates some confusion if we use Greek letters for angles and English letters for sides. So if I ever get a letter, or I get a problem that uses capital letters for angles, I just change the whole problem to Greek letters. Just cross it out and change it. All right, so now let's find a couple things in this diagram. Let's find the sine of alpha. Okay. What's the sine of alpha going to equal in that diagram? A over C. Yep. Now, I'm going to make up another problem, but I'm going to do it in a very specific way. First, I'm going to put the word co in front of them. What function do I get if I put co in front of that?
Cosine.
Cosine. That's called the co-function. When you put the word co in front of a trig function, that's its co-function. So I'm going to start by writing the co-function of that. Cosine. And I'm going to pick an angle here that is complementary to alpha. What angle is complementary to alpha in that diagram?
Beta.
And that's what we just set up here. Okay, beta. So I did two things. I found the co-function of that, and I found the complement of that. And let's see what happens. What is the cosine of beta?
A over C.
Adjacent over hypotenuse. Yep. They come out exactly the same. Okay, let's do another one. Tangent of alpha. Okay. What's the tangent of alpha?
Cotangent of
Well,
beta.
yeah, it's A over B. And that's going to be the same as something else. Does anybody know what else also comes out to A over B?
Cotangent theta.
Put the cotangent in front of that, or put co in front of that, so cotangent. And what did you say for the angle?
Beta.
Beta, yeah. Those two things come out exactly the same. How about a numeric one? Let's do the sine of 15 degrees. I don't want to know what that is. It's a decimal. I want to know something else that is equivalent to it. Yeah?
Cosine of 75.
Yes. I still don't know what either one of them are, but I know that they're equal. So let's just check it. Here's the sine of 15. Here's the cosine of 75. They're exactly the same thing. So these are complementary angles, and those are cofunctions. So this is called the complementary angle theorem. If you have cofunctions, and just in case we're not clear what those are, sine and cosine are one pair. Secant, cosecant, that's another pair. Tangent, cotangent. So it's a little bit different pairing than reciprocals. Tangent and cotangent, though, are both. They are reciprocals of each other, and they are cofunctions. But the other ones, they're paired up a little differently. Sine, cosine, secant, cosecant. So if you have two cofunctions and complementary angles, then the expressions are equal. So how could that help us? Well, let's say you had something like that. I don't know what either one of those are, okay, because they're not multiples of 30, so it makes it 45, so it's very hard to do in my head. But I don't need to know that, and I don't need to know that to figure out what's going to go in that box. If you're trying to figure out this and this to find that, you're not thinking about it the right way. I want to think about what we know about each one of those things compared to each other. What do we know about the sine of 35 and the cosine of 55?
Complementary.
They're what?
Complementary.
Well, the 35 and the 55 are complementary. Yep. What else do we know?
They come up with the same answer.
Yeah, the sine and the cosine are cofunctions, which means we can apply that theorem. So how does the sine of 35 compare to the cosine of 55?
Equal.
They're equal. You're subtracting two things that are the same. I don't need to know what the things are I'm subtracting. That doesn't matter. I just know I'm subtracting two things that are the same. What does that mean I'm going to get?
Zero.
I'm going to get 0. Now, does that trick work with addition? Like if you add two things that are the same, do you always get 3? No. With addition, you get that thing doubled. So this doesn't help you with addition, but it does with subtraction. What other operation do you think this idea would help us figure something out?
Division.
Division, yes. Okay. What do we know about tangent and cotangent?
Cofunctions.
They are cofunctions. What do we know about 20 and 70?
Complementary.
They're complementary. We have cofunctions of complementary angles. What does that mean about what's in the top and what's in the bottom? They're equal. Okay, I don't know what either one of them are, but I know they're equal. So what does that mean is going to happen here? We get 1. So what I'd be more interested in a problem like that is why the answer is 1. Not that you got 1, but the reason behind it. Because they would just type that in. But the complementary angle theorem tells us why. Would that help with multiplication? When you multiply two things that are the same, do you get the same number? No, you get that thing squared. So it really is only a shortcut in a very specific situation, and it has to be subtraction or division. Okay, any questions on that? All right. So that's the first part of 6.1. So most of the homework is in the book, but I also want you to simplify sine 40 over cosine 50 and tangent 35 minus cotangent 55. Okay, you've got just over 20 minutes left, so you've finished up a little early. So please use the time to try to work on something. If you have any questions, you get stuck on anything, I can help you.
Yeah,